Um, Thanks, Priya. Thank you, Mr. Suni, for chairing the session. So, um, in this presentation, I'm just going to give you a really high-level sort of preliminary results on analyzing battery storage. So, as Mr. Suni said, storage, there are plenty of value streams. But the modeling exercises that we did, we are basically looking at only energy arbitrage and peaking capacity. Okay, we are not looking at other value streams like from storage, such as transmission deferrals and black start capability, etc. And this particular study, we have done it with my colleagues Anna Mileva from Blue Marble Analytics and my colleagues from Prayas Energy Research Group, Ashwin Gambhir, Srihari, and Shantanu Dikshit. So I'm going to acknowledge them. Okay, so largely we all are aware of our goals. 175 gigawatts by 2022. Some of the CEA numbers that are coming out are putting out 400 to 500 gigawatts by 2030. So what we wanted to look at was what are the most cost-effective pathways to meet these goals, and then what is the role of energy storage in this? So we're basically looking at cost and technical capabilities of all these technologies. Two main things that we want to look here in these scenarios are cost trajectories for renewable energy and cost trajectories for energy storage. And these are all lithium battery prices. So if you look at the top chart here, these are prices for battery storage 4 hours. And these costs are from NREL's annual technology baseline study, which came out in 2019, just recently. So the cost trajectory that we are considering, there are two cost trajectories for each of these technologies. In 2018, the cost of energy storage, especially in the US, was about 370 per kilowatt hour energy capacity. So on the y-axis, you're seeing the prices per kilowatt. Okay? For solar PV and wind, the prices were about $60 a watt for solar and about 88 rupees per watt for wind and 60 rupees per watt for solar. These are average prices in the 2017-18 auctions. And we took that initial price and then the two cost trajectories, the high cost RE, we didn't change the real cost until 2030. And the low cost RE, we assumed 5% per year declination for solar PV and 3% per year for wind. These are very similar to what we're seeing in the NREL's annual technology baseline. Okay? So what we're going to do in our models are change these particular values. Now let's talk briefly about what kind of model we have developed. And the reason for this particular paper was also to showcase the capability of this modeling platform that we are developing. And we're going to release it as a free and open source modeling platform. The important part is also free because you don't need any license for the modeling language. Like we're not using GAMS, we're just using PyOmo. You can use a free solver, and this will be available to researchers or anybody who wants to use it within the next few months. So what is this model? This model is called GridPath, and it's a capacity expansion and production cost model, although for this particular study, we have only used the capacity expansion mode. So what does it mean, right? What this does is it simultaneously optimizes the capacity investments and operations costs, okay, for different projects, subject to operational and policy constraints. Okay, so you can put a policy like an RPS, a renewable portfolio obligation constraint, or a carbon cap, whatever the modeler sort of wishes to do. So in this particular model, we have put in like different targets for renewable energy penetration. And the model optimizes over 4 different capacity investment periods, 2018, 2022, 2026, and 2030. So our target is to look at what happens in 2030. And then in each of these years, we sampled 1 day per month and 24 hours for that particular month. So you have to sample these points in these models because otherwise, if you use like an 8760 model, the model becomes really big, it becomes intractable. So the idea is you sample these points, sample your wind and solar data, as well as existing and new generators. You put it all into one optimization problem, and the model will choose what capacity you want to install to meet your renewable energy target at the least cost. Okay? And this is a single node model. The modeling platform has capabilities of adding transmission capacities as well. But this particular iteration, we just have a single node model for India. So it's a copper plate. Okay, and the results that you get are basically what kind of generation capacity and storage capacity you want to invest in. You can also guess costs and dispatch, but let's focus just on the capacity and energy generation results from this particular study. Okay, so again, there are 4 main scenarios with 4 different RPS targets. RPS meaning Renewable Portfolio Standards, but it's the same as Renewable Portfolio Obligations here. And we looked at 10%, 30%, 50%, and 70% targets. And this is only wind and solar energy, not biomass, not hydro. If you add those, the percentage will go about 10 odd percentage points. Okay? Within these 4 scenarios, there are again 4 sub-scenarios. And these play with the 2 different cost trajectories for storage and renewable energy. So going from left, we have the high-cost renewable energy, high-cost storage, high-cost renewable energy, low-cost storage, low-cost renewable energy, high-cost storage, and low-cost renewable energy, low-cost storage. Okay, so we have total 16 scenarios in here. All right, so let's look at the results. This is the new capacity build-out in 2030. On the y-axis, we have new capacity, and on the x-axis, we have the cost scenarios. So let's see what insights we can glean from this particular exercise. First, when renewable energy costs are low, but still realistic, right? We are only assuming 5% declination for solar PV and 3% declination for wind. Then, in the 10% and 30% RPS cases, we are seeing about 400 to 440 gigawatts of renewable energy being built cost effectively. Okay? One of the later charts I'll show that this RPS constraint is non-binding, which means just using those particular costs, we are seeing energy penetration much more than 10 and 30%. We are seeing about 40% penetration. So this result is very similar to the CEA recent analysis that came out. All right, so that's insight number 1. Insight number 2, for 50% RPS, we are seeing about 550 to 560 gigawatts of renewable energy, so much more. And for 70% RPS, it's about 850 to 950 gigawatts. Okay, so pretty high capacities. Now, when renewable energy costs are low, okay, which is basically the last 2 bars in each of these charts, then no new coal was built across all cost scenarios. Okay? This is an interesting insight, but I don't want you to be too attached to it. This is not an 8760 analysis, so there might be some time periods that we are not sampling where wind and solar are so low that we need some kind of firm capacity and maybe battery capacity is not built. But still, we know that during those cost trajectories, coal is not going to be built much. But intuitively, I mean, it makes sense, right? You have low-cost RE, you want to build more of that, and demand for coal is going to go down. Okay. Now, for the 10% and 30% renewable energy targets, battery storage is built only when both VRE and battery costs are low. So it's just this last bar. And here, battery is basically in this red color, is this little sliver up here, okay? So only when both battery costs and renewable energy costs are low, that's when batteries are built. When only battery costs are low, but renewable energy costs are high, battery storage is not built for the 10% and 30% RPS targets, so lower penetration. And this is like at the 40% renewable energy penetration levels. But at the higher targets of 50% RPS, battery storage is built when battery costs are low. So you're going to 50% RPS, you need battery storage to balance. And with that low-cost battery storage cost trajectory, batteries are cost-effective to be built for balancing renewables. And at the higher 70% RPS target, battery storage is built across all scenarios. So this is the red part in all these bar charts. Okay? All right. Next insight, greater shares of renewable energy increases the value of energy storage. What does that mean? So if you are targeting higher renewable energy targets, right, or goals, then more battery storage is built. So that is also intuitive. As we go from 10%, 30%, these are obviously 40% RPS scenarios. 50% and 70%, the amount of battery storage that you need is going to go up. But greater storage capacity increases the share of solar PV within the renewable energy targets. So if you look at these particular, so let's compare this scenario, this low-cost storage scenario with the high-cost storage scenario. See the proportion of blue bar versus the orange bar. In each of these bars, the share of wind goes down and the share of solar goes up. If you compare these two, again, the share of wind goes down, solar goes up compared to this bar. And similarly for these particular 70 scenarios. So solar energy gets a boost when storage costs are low and you build more storage. That's another interesting insight. And that is to do because of the variability of solar and the variability of net load. It's just predictable during the day because solar is diurnal, the variability is diurnal, and the amount of value that storage can provide through energy arbitrage is much more in the storage scenarios than the wind scenarios. All right. Now let's quickly look at the energy generation shares in each of these scenarios. So you will notice on the y-axis it's 0 to 100%. So these are shares of energy generation to meet demand. Some of these bar charts go above 100%. That's because we have curtailment of renewable energy. So all the dark red parts of the bar chart go above 100%. Okay? Some areas are below 0%, and those are battery losses. Okay, so that's how you should read this chart. So one of the insights that I shared earlier, if you have a 10% and 30% RPS constraint, when renewable energy prices are low, then you're hitting about 40 to 44% renewable energy shares in electricity generation cost effectively. So that constraint is not binding. Okay, it's cost effective to go up to 40% and build about 400 gigawatts of renewable energy. Next insight, so renewable energy curtailment increases with high RPS targets. So that's intuitive. We have more renewable energy. It's going to increase. And here you will see that through these dark red bars, these are much higher in 50% and 70% RPS targets. Now, it looks low here. Once we have transmission constraints in the model, you will probably see more curtailment. Okay? But storage reduces renewable energy curtailment. That's also intuitive, but we can model this. So whenever we have storage, which is in the low-cost storage scenarios, you will see the red part of curtailment go down compared to less storage. So all these things that were intuitive, we can quantify it through such modeling exercises. All right, my last chart. In our model, we did not specify whether the model should build a 4-hour battery or a 5-hour battery storage. We didn't specify any of that. We had two different costs, one per kilowatt and one per kilowatt hour of battery storage. And the model optimized how much duration of battery storage we would need cost optimally. So, oops, sorry about that. So this chart, on the x-axis, we have storage energy capacity in megawatt hours. And on the y-axis is storage power capacity. Okay, so the ratio between that is the duration. In all these scenarios, whenever storage was built, we were getting about 5 to 7 hours of battery storage. That was the requirement, optimal requirement, which is close to 4 hours, but based on the wind and solar profiles and the load profiles in India, the most optimal sort of storage duration was between 5 and 7 hours. So this gives us a good insight on what kind of storage we want to encourage from the market. All right, so my conclusions: low-cost battery storage will be crucial to cost-effectively transition India towards deep decarbonization. And the value of battery storage will increase when benefits beyond peak capacity and energy arbitrage are considered. So when we consider benefits from reserves, which we can model in this particular modeling platform, we just haven't yet. But reserves is one. So that's ancillary services, but transmission and distribution deferrals, if you can incorporate that as well as black start capability, that will just increase the value of storage. And the last part is results will improve, like of this modeling exercise, once we have transmission constraints, constraints on ancillary services, as well as planning reserve margins. So these are very preliminary results, but the insights, the large, high-level insights, are less likely to change. With that, thank you.